Hello everyone. In the first class, we'll be talking about some very basic facts about the Earth and about the Earth's position in the solar system. So before we kickstart the class, I'm going to go forward with the assumption that we all have some very basic understanding of what the Earth looks like, what the countries on the Earth look like, and some very basic terms that we've used in everyday life. So, firstly, we all know what the direction east is, right? We say Japan is to the east of India. We say Dubai and South Africa is to the west of India. Antarctica is to the south of India. Russia is to the north of India. Now, when we define these directions, this is where we encounter our first problem. It is about how do we scientifically define this. So, to solve this, what we say is that first we define that the Earth, we reference this to the Earth's rotation. Let's say that. So, we say that the Earth rotates from west to east, right? Then, the direction of rotation, if we go in the direction of rotation of Earth, that direction we term it as east, and if we go opposite the rotation, we call it west. Okay? North and south are relatively more simple. So we have a line joining the point from North Pole all the way going to the South Pole, right? So the direction on the Earth's surface, if it is going to the top, it is north. If it is going to the bottom, it is south, right? Now, because I mentioned that the Earth is rotating, the Earth was essentially a gas cloud. So because of this rotation, what happens is that because of the centrifugal force, the Earth happens to bulge out a little, right? So this is where we encounter our second problem, that the Earth is not an exact sphere. It is not what we call it to be a sphere. It is what we call as an oblate spheroid. If I were to draw an exaggerated figure, this is what it would look like. This is called an oblate spheroid, right? An oblate spheroid or an ellipsoid, that is what it is called. Okay. So this is a sphere which is slightly flattened at its poles and slightly bulged at the equator. Why is this? This is because of the centrifugal force which is acting because of the rotation of the Earth, which was from west to east. Right? Now, when we're talking about this, there are two terms which I want you guys to understand and know. We have something that is known as the minor axis, that is going all the way from our North Pole to our South Pole, and we have something that's known as the major axis, right? So, this is known as the minor axis, right? And this axis is known as the major axis. Fine. So the minor axis is smaller. The minor axis is smaller than the major axis. Okay, this is very evident with the diagram we've drawn because the Earth is squished, okay, from the top, from the poles, and it is bulging from the sides. Think of like a ball that you press vertically downwards, along the poles. So we have another term which we call about and we know as the compression ratio, right? So what is the compression ratio? The compression ratio is the difference in the diameters, or let's say the difference between the major axis and the minor axis to the major axis. It is the ratio. So what we are essentially saying is that by how much is the minor axis smaller than the major axis. So when we calculate this, we get 1 by 298. So the minor axis is smaller than the major axis by 1/298 times of the major axis. For our convenience, we approximate this to 1:300. Okay, what this means in so what does this compression ratio mean, right? So I've already said that it gives you a value as to by how much is your minor axis smaller than your major axis. The minor axis is smaller by 1/298th of the major axis, or another way to write this would be that the minor axis is equal to major axis minus major by 298, right? So this explains the compression ratio. Now in aviation, for our reference, because we use all the equipments like GPS, we use intricate instruments like GPS and many other navigational equipments, we have to assume the shape of the earth to be something. Now the shape of the earth is not really constant. Okay, if I were to give you a reference, the shape of the earth looks relatively more like this. Okay, it's not even a perfect sphere, it's a bulged out sphere, but it's also uneven, right? There are elevations on the earth, there are depressions on the earth, so it's not really even. So to make and design an accurate system such as the GPS, we had to adopt a model for the worldwide application. This model was called as the World Geodetic System, and it was developed in 1984. So this is called as the WGS 84. Okay? So ICAO has adopted the WGS 84 as the world standard. Now, modern navigation systems automatically correct position information for distortion of this Earth's shape. Right. Now, the circumference of the Earth, if we were to consider it to be a true sphere, okay, the circumference would have been 2100 nautical miles, 21,600 nautical miles, sorry, or what we know as 40,000 kilometers. Right? So please remember this kilometers value, right? So the circumference of the earth, if we were to consider it, okay, now it's extremely, the bulge, like I said, in this diagram was extremely exaggerated. The bulge is ever so slight. It's 1 of 300 parts, slightly different, right? We just saw that in compression ratio. So if I were to assume it to be a literal sphere, then the circumference was 21,600 nautical miles, or what I calculate as 40,000 kilometers. So I want you to remember this number. Then, okay, so moving forward, there are two other terms which we will have to go about. One is called the great circle, and the other is called a small circle. Okay, so a great circle, let's understand this. If we were to cut discs of the earth, right, then if we were to get a disc such that it passes through the point of intersection of both the major axis and the minor axis, which is basically the center of the earth, right, of a sphere, if we were to draw the major axis and the minor axis, they both will intersect somewhere. That will be the center of that sphere. So if this disc were to pass through that center, then we call that to be a great circle. Okay, this is a geodesic disc. If it does not pass through the center, then we call that circle as a small circle. Now, why is this interesting? It is because we say that if we were to travel any distance along this great circle, then this is the shortest distance between 2 points. So in other words, if I were to travel between 2 points on the surface of the earth, right, then the shortest distance between them will be a part of a larger great circle. Okay, now what is a great circle? A great circle is a disc which were to pass through the center of the earth, and the extremities or the perimeter of this circle lies on the surface of the earth. if we were to travel between 2 points and take the shortest path between them, then this shortest path would be a small portion of this very large great circle, right? What I'm trying to say is that this could be point A and this could be point B. This is the shortest path between them, right? This is when I'm looking at the top-down slice which I've drawn, right? And if there is any other circle which does not pass through this center, it is known as a small circle. So let me show you what it looks like on the Earth's surface. Now see this. Now, we both can see that they pass through the center of the Earth, right? All these disks. And we can have infinite amount of great circles drawn on the Earth, right? There's no end to it. We can draw an infinite amount of disks passing through the center of the Earth. Similarly, if I were to say that I was to travel from point A to point B, the shortest distance between them, like I said, is a part of a much larger great circle, right? You see it here, right? Then, anything else which does not pass through the center is known as a small circle, like this. It's very clear from the way this circle is cut out that it does not pass through the center of the Earth, right? So this is what we call as a small circle. So now let's quickly look at some properties of great circles, right? So what are some properties of great circle? So firstly, we've already discussed that these are the shortest distances, right? So these are the shortest distances on the Earth's surface measured between 2 points. 2 points. Then, second, when viewed on the surface of Earth, it appears as a straight line. Right? Then, any 2 points on the Earth's surface can have at least one great circle passing through them. Right? Any 2 points on the Earth, you take it anywhere, right? Even if I were to consider 2 points here, A and B, right? There's at least one great circle that will pass. If I were to take 1 point here and 1 point here, A and B, right? There's at least one great circle that will pass through them, right? Again, now if the 2 points are diametrically opposite, if 2 points are diametrically opposite, I can draw infinite amount of great circles, right? This is what it means. I can draw an infinite amount of great circles if my 2 points were to lie opposite to each other, right? This is very easy to visualize. If you were to visualize that we have 2 points, let's say here, right? And we have another point here, right? I can draw an infinite amount of great circles passing through them, right? Fine. So as long as my 2 points are diametrically opposite, I can draw an infinite amount of great circles, right? I could draw it like this. I could draw a great circle like this. I could draw a great circle like this. So on and so forth. I could draw an infinite amount of great circles passing through 2 diametrically opposite points. If the points are not diametrically opposite, then I can at least draw one great circle passing through them, right? Fine. So something very important to realize is that when we draw a circle on the earth, it appears to be a small straight line. Now, if we were to draw the same great circle flattened out on a map, the great circle would appear to be a curved line. Okay, this is just a fact. We'll be discussing this in a little more detail after this. Now, let's look at the earth more in a space point of view, right? So, the earth rotates in what we call as the orbital plane. So the earth is just one of the planets in our solar system that orbits the earth, that orbits the sun, right? This is our earth and it orbits the sun. This orbit itself is completed on the plane of the ecliptic or the orbital plane, which is essentially this plane, right? This plane of revolution is what we call as the orbital plane. Now, this figure is definitely not to scale, but it gives you an idea of what the movement of the planet is, right? Now, what you also need to realize is that the earth also rotates about its own axis, right? So we spoke about it that the earth is rotating from west to east, right? The earth is rotating from west to east. So when we are viewing from the north pole, the earth is rotating anti-clockwise, and when looking at it from the south pole, the earth is rotating clockwise, right? So the spinning of the earth around its own axis is called as rotation. Spinning about one's own axis is called as rotation, right? And thus the earth is rotating on its own axis while it is also revolving. It is also revolving around the sun. So the earth is also revolving from west to east, right? It's going around the sun anti-clockwise, right? So the property of earth going around the sun is called as a revolution, and the one that is rotating on its own axis is called as a rotation, right? Now, the poles of the earth are defined because the earth is rotating. It is rotating about some central axis, right? Like your bicycle wheel, it is rotating about the center where all the spokes connect, right? It is rotating about the center. Similarly, the earth is also rotating about an axis. Where this axis passes through the surface of the earth, we call it a north pole. And where it passes to the bottom of the earth, we call it a south pole, right? In other words, the poles are defined as the extremities of the axis about which this earth spins, right? And this axis is not essentially vertical, okay? Now please understand that the space itself does not have any up and down and west and east. It does not have any direction. When I say space, I mean the whole universe has no direction as such, right? So what I need you to understand is that this axis is not exactly straight or how we draw it on paper. It is slightly inclined, right? The earth's axis is slightly tilted. Now, like I said, if there is no direction, it is tilted in reference to whom? It is tilted slightly in reference to what our orbital plane is. So, the tilt is between our orbital plane and our equatorial plane. We have this as the Earth's equator, and we have this as the orbital plane, right? So the Earth's equator is not exactly parallel to the orbital plane, rather it is at an angle. And how much is this angle? This angle is 23.5 degrees. This angle itself is what we call as the tilt of the Earth's axis, or this angle, right? This angle also comes out to be 23.5 degrees. And this angle is extremely important because it is this angle because of which we have our seasons. So seasons are because of the tilt of the earth. Let's take a moment and understand this, that why do I say that this is because of the tilt of the earth. So if you were to look at this diagram here, right, because the earth is tilted, right, the earth is tilted, and tilted in reference to whom? Tilted in reference to this orbital plane in whichever it is rotating, right? This is the orbital plane it is rotating in. So as in when this earth keeps traveling, it keeps going westwards and it makes this anti-clockwise circle, you'll see that different parts of the earth are heated differently, right? Because of the tilt, there is a time when majority of the sun's radiation is experienced by the southern portion of the earth, or the southern hemisphere experiences more sunlight, or what we call in aviation as insolation, right? The southern part is receiving more of the sunlight, right? It's closer to the sun than the northern part, and this whole brief part at the top receives no sunlight at all, right? Similarly, the earth continues, and the whole face of the sun gets more light. Then there comes a time around June when the northern hemisphere is getting more sunlight from the sun, right? So this hemisphere is turned to the sun during the month of June or July. Then again the sun continues its journey, and whole face of the sun is getting heated up again. So in winters, the solar energy is spread over a larger area, making the whole area weaker in terms of energy that it is receiving. And in summer, more energy is concentrated in these areas. So we can say that during December, the southern hemisphere is experiencing what we call as summer, and during June, the northern hemisphere is what is experiencing summer, right? Fine. Now when this happens, because of this uneven heating, now if you see that one part of the earth, one section of the earth is getting heated up much more opposed to the other sections. The southern hemisphere is receiving very little light here, right? There's a whole portion of the earth that is not receiving any light. It's extremely away from the earth's surface, from the sun's surface. So this creates a disbalance, or it creates an uneven heating on the earth's surface. This uneven heating gives rise to winds, it gives rise to pressure patterns. These pressure patterns further is what causes weather, right? And this weather, when it is a very periodic change, is what we call as seasons, right? So it is basically because of this tilt. If the tilt had not been there, let's imagine that the tilt was not there, then half of the earth would receive sunlight at all times, right? And the other half would be in dark. But as and when the earth revolved, overall half of the earth at any given time would be receiving great sunlight and half of the earth wouldn't. As and when the day passed, in the cycle of a day, everyone would get the same amount of heat, and there would be no temperature difference along different surfaces or different regions of the earth. If there were no different temperatures and different portions of the earth, then there would be no flow or wind being created. If there was no wind or wind patterns being created, rather, there would be no seasons as we know it, right? So the seasons are purely because of the tilt of the earth. I want you to take a moment and observe this picture, right? Now, because of this tilt, we have a very interesting phenomena also, right? This is known as the winter solstice and the summer solstice. So what is this, right? So you must have read this term earlier on. So let's talk about this, right? Because the earth is not exactly straight, it is at an angle, right? We spoke about this. The earth is at an angle, it's not exactly straight, right? The earth's axis is at a slight angle. And how much is this angle? This angle is equal to 23.5 degrees. So if you think about it, okay, let's take a moment and draw something. If the earth was straight, right, let's say the earth was straight, and we had the sun here, right, we had the sun, right, then what would have happened? We would have had maximum heat being experienced at the equator, because the equator was something that was closest to the sun compared to the poles, right? Because the equator was closer, it would have experienced more sunlight, and that would have led to it heating up the most, right? Fine. But because of this tilt, what happens is that the portion of the earth that receives the maximum sunlight, right? The portion of the earth that receives the maximum sunlight is decided by the position of the earth around the sun. Let's understand why do I say that. Because if this is my equator on the earth's surface, right, and this is my axis, which is tilted from my vertical axis by 23.5 degrees, then the maximum sunlight now will be received by some point which is here, right? And how high will this point be? This point will also be at 23.5 degrees, right? Similarly, when my earth were to cover a whole revolution around the sun, and finally this same sun were to now be on the opposite side, or rather this side, who would be receiving the maximum sunlight? Some point which is here, right? It would be some point which is here. Please mind that the earth's equator is here. Okay, this is the earth's equator. Okay, and this is the North Pole and this is the South Pole, right? So some point here would be receiving the maximum sunlight, and this would also be at an angle of 23.5 degrees, right? Now, if you were to observe this picture, you'll realize what I'm talking about. Right now, this position is what diagram I had drawn first, saying that 23.5 degrees north would be where the sun would be maximum in this case, and in this case it would probably be 23.5 degrees south. So when the sun is at its maximum or the southernmost position that it can ever be, right, depending upon the position of the earth in its orbital plane, I call that as the winter solstice. This is where the days are going to be the longest, okay, because the sun is at its maximum deviation from the equator southernwards, and this line is known as the Tropic of what? I want you to comment and tell me what this line is called. Similarly, when the sun is above the highest point in the northern hemisphere, that is again going to be at 23.5 degrees north, right? We call these lines as the Tropic of Cancer and the Tropic of Capricorn. And there's a reason why we call this as the tropic, because these lines mark the maximum boundaries of the sun, right? So the sun goes, now it's very interesting, the sun goes through this whole cycle of maximum and minimum. So if I were to draw a graph of the sun's movement, right, let's say that this is a year passing, okay? This is, let's say, the months of a year. This is the months, and this is 0 degrees equator. This is north, this is south. So the sun starts at the equator. As and when the earth is rotating, it climbs up to a maximum of 23.5 degrees north, after which it comes down again to the equator, then further goes down south to 23.5 degrees south, only to come up further again, right? So these boundaries mark 23.5 degrees north and 23.5 degrees south. So the sun, every time it crosses the equator, whenever the sun is over the equator, I have equal lengths of day and night, and these points are known as equinox, right? Equinox. And these points are known as solstices, right? So take a moment and understand this with the position of the earth. So we have our winter solstice, which occurs usually on December 21st. This is when the sun is at its maximum southern position, or what I call, now if I were to draw it here, the Earth's equator is like this, right? But looking at the orbital plane, you can easily tell that the sun's maximum radiation is at some point here. And this point is nothing but 23.5 degrees south. Similarly, the Earth were to travel, and right now the sun is over the equator, right? This is when we have a spring equinox. This is usually during March, on March 21st. After this, the sun starts moving northwards, right? So it came from the south and it is now moving northwards. During that course, it crosses the equator. When it is crossing the equator, I call it an equinox. Further, when it is moving north, it goes and stops at its maximum northernmost position. Again, let's draw the equator, right? We have some equator and we have some line here, right? This is again 23.5 degree north, right? So now the sun is again at its maximum height or maximum latitude, right? After that, the sun again travels down, right? It starts moving southwards, or rather the sun doesn't move southwards. It's because of the revolution of the earth around the sun that the sun happens or appears to be shifting downwards, right? Then we have an autumn equinox where the sun is again at the equator, right? So I hope this corresponds with the graphs we've drawn, right? We have the two solstices and we have the equinoxes. Fine. Now, moving further, we have a term which you'll come across, which is known as declination. Okay, now what does this term declination mean? Let me just write it down. Declination, right? So the term declination is the angle that the sun is above or below the equator. Okay? The angle the sun is above or below the equator. It is this angle that decides the length of day versus night, right? It is this angle that decides the length of the day versus night. Now, the maximum position it can have, the sun's declination. Okay, if I were to say it, the sun's declination changes between 23.5 degrees north to 0, followed by 0 to 23.5 degrees south, back to 0, from there back to 23.5 degrees north, back to 0, and so on so forth. The cycle continues, right? Fine. So 23.5 degrees south is known as the Tropic of Capricorn. 23.5 degrees north is known as the Tropic of Cancer. Now, very interesting, let's study about the Kepler's law. So now, Kepler was a scientist, right? Kepler's law. So Kepler was a scientist who proposed two laws. The first was that the orbit of each planet is an ellipse and the sun is at one of the focus. Okay, so the first law of Kepler says that the orbital path is an ellipse and the sun is at one of the foci. Okay, what that means is the earth is not traveling around the sun in a circular path, right? This is the sun. The sun also lies at one of the two foci of the ellipse. From school we remember that ellipses have two foci and the earth is rotating. Okay, let me draw the earth in blue. Okay, the earth is rotating around this ellipse in an elliptical path with the sun at one of its foci, of the two foci that they can be F1 and F2. The sun, let's say, is at F1. Fine. So when the earth is the furthermost away from the sun, it's called as a aphelion. Okay, this position is known as the aphelion. And when the earth is the closest to the sun, okay, when it is on this side or closest to the sun, this position is known as the perihelion. Okay, so it's known as the perihelion when it's closest to the sun, and aphelion when it is furthermost away from the sun. The second law of Kepler states that a line joining the planet and the sun sweeps what? Does anyone recall? Equal areas in equal time. Okay? So the Kepler's second law says that if there is a line joining the planet and the sun, it sweeps equal areas in equal times. So now this is again a very interesting concept. So let's say that this is the orbital path. Okay, this is the orbital path. We have the sun at one of the foci. So let's say we have the sun here and we have our earth, right? So if I were to take a line joining the earth to the sun, okay, in the course of the earth's revolution, the earth would sweep an equal amount of area. Okay, so let's say the earth was here and the earth was here. All of this area that you see, both of these areas would be equal. Now you say, how is that? Right? Visually also, if you were to see this, you realize that, okay, it's not going to be equal. The only way for this were to be equal is if this pizza slice was much larger or it was wider. How is that? That's going to happen if the earth is traveling faster when it is at its perihelion, right? So the earth rotates or revolves faster, or it crosses this path at a much faster speed than at what it is revolving here, right? Only in that case will they both cover equal areas in equal time, right? So the earth travels faster when it is at its perihelion and it travels slower when it is at its aphelion. Okay, so let's quickly summarize what all we've studied so far. So we started with what we defined the earth. We defined what east and west was. We also spoke about how the earth was not a sphere but rather an oblate spheroid. An oblate spheroid is a sphere which is slightly squished from the top and slightly bulged on the sides. Why was this? This was because of the centrifugal forces forcing the extremities of the earth slightly outwards. Then we have two axes. One is the axis connecting the North Pole to the South Pole and passing through the center of the earth. This is known as the minor axis. And we have another axis which is passing along the equator, which is known as the major axis. Both of these intersect at the center of the earth, right? Because we're talking about a sphere. The minor axis is smaller than the major axis. Now, we find a ratio of how much more smaller it is. By how much is it smaller? So when I calculate this, I get 1:298, which I approximate for aviation purposes. I use a ratio of 1:300. What this means is that the minor axis is 1/300 times of the major axis smaller than the major axis. It's 1/300th of the major axis smaller than the major axis itself. A different way of understanding this is that the minor axis is equal to the major axis minus 1/300 parts of the major axis, right? So if the major axis were to be 300 units, the minor axis would probably be 299 units, right? That's what we say. Fine. Then we also spoke about how practically if you were to look and realistically if you were to look at the earth is not an exact sphere. It is not even exactly an oblate spheroid. It is rather this one uneven geoid. Okay, that's the actual term. It's called a geoid. But because we have GPS systems, we assume it to be a sphere, right? And this sphere, its circumference when we measured, it came out to be 21,600 nautical miles or 40,000 kilometers. This model, we had to construct some model to program our global positioning systems and to program our other navigational systems. So that model which we created and which got accepted by ICAO is known as the WGS-84 or the World Geodetic System, which was made in 1984, right? Then we spoke about what great circles were. Great circles were, let's imagine that we were to cut a disc, something like a CD disc. If we were to cut a disc or slices of the earth, the slices that pass through the center of the earth, right? These discs were known as the geodesic discs, right? And the extremities or the circumference of these geodesic discs on the surface of the earth are what we call as great circles, right? So a great circle is a circle that divides the earth into two equal halves, right? And to divide it into two equal halves, it's very clearly understood it has to pass to the center, right? And anything that does not pass to the center is known as a small circle. Fine. Now, this circle which is drawn on the surface of the earth, which separates the earth into two equal halves, also happens to be the shortest distance between any 2 points, right? So how do we understand this? We went back to what we studied during school, that the shortest distance between any 2 points, any 2 arbitrary points, is a straight line. And a straight line on the surface of the earth, if I were to extend both the ends, right, and continue extending them, they would ultimately follow the curvature of the earth and come and join their ends, right? And this would ultimately form a great circle. So this is what a great circle looks like on the surface of the earth. Here we can again observe that it passes to the center of the earth. And again, any distance between point A and B, the shortest distance will be along the great circle path. Then we studied some properties about the great circle. It is the shortest distance on the earth's surface, which is measured between 2 points. When viewed on the earth's surface, it appears to be a straight line. Any 2 points on the earth's surface can have at least one great circle passing through them. And if 2 of these points which you want to measure, if they are lying diametrically opposite, then there are infinite amount of great circles that can be drawn. Then we also saw what a small circle looks like. A small circle is what an Arctic Circle or a Tropic of Cancer, if I were to cut a disc along the Tropic of Cancer or a blade slicing along the Arctic Circle, this would create small circles, right? Fine. Then we spoke about the orbital plane of the earth, how the earth is rotating in this one elliptical plane around the sun, right? And this is known as the orbital plane. Now, while we are rotating in this orbital plane, we realize that, okay, there are no directions in the space, right? There are no directions in space. But if I were to reference myself along with the plane or the orbital plane, then my equator is not exactly perpendicular to the orbital plane, but it's slightly skewed, right? So it is slightly skewed, right? It is skewed by an angle of 23.5 degrees. It is because of this tilt that we have seasons. It is because of this tilt that some portions of the earth get heated up slightly more than other portions. It is because of this uneven heating that we have seasons. It is because of this uneven heating, which is itself in turn because of this tilt, why we have weather systems and weather patterns blowing around the earth, right? And this picture explains it as to how, depending upon the position of the earth, different hemispheres of the earth receive different amounts of sunlight. Then we also spoke about how during this one whole year that it takes for the earth to revolve around the sun, we have different times where the sun is closest in the southern hemisphere and is closest to the northern hemisphere. Because of the earth's tilt, the highest and the lowest position when measured from the equator that the sun can be is measured to be 23.5 degrees south and 23.5 degrees north, right? These are called the Tropic of Cancer and the Tropic of Capricorn. There are also two times during the revolution of the Earth, that the sun passes the equator. When it is over the equator, both the durations of my day and night are equal, and these are known as equinox. There's a spring equinox, there's an autumn equinox, and there's a winter solstice, and there's a summer solstice. If we quickly look at the graph, you'll see that the sun goes from a period that it is over the equator. It goes from a period that it is over the equator, goes to its highest position, which is here, then again continues to come back, or the earth rather travels around the sun such that its sunlight were to be maximum at the equator, and further it goes to down south, and the sun, in our view as the earth, travels back to the equator, right? Then we spoke about a term called declination. This is the angle that the sun is above or below the equator. This angle decides the length of the day and night. It decides the proportion of how long the days are going to be when opposed to the night. Sometimes we have longer days and shorter nights, and sometimes we have longer nights and shorter days. Equinoxes, both our days and nights are equal. So, this angle that the sun makes above or below the equator is known as declination. So, the sun's declination changes from a maximum of 23.5 degrees north back to zero to a minimum of 23.5 degrees south back to zero, again 23.5 degrees north to zero, and so on and so forth. The cycle continues because the earth keeps revolving around the sun. Then we sorry. Then we spoke about Kepler's law of planetary motion. In this, we spoke that the orbital path of an ellipse of a planet is an ellipse, right? And the sun is at one of the foci of this. The second law said that if we were to draw a line joining the planet to the sun, then this line were to sweep equal areas around the sun in equal amounts of time. Now, when we draw the diagram, we know that the earth is closer to the sun at the perihelion and is the furthermost away from the sun at the aphelion. So, in order to cover the same amount of area and same amount of time, the earth has to travel faster when it is at its perihelion, right? And this explains you the very basics of what I expect you to know. This creates a very simple foundation to what we're going to study further. Please go through this. If there are any doubts, let me know in the comment section, and I'll see you in the next class. If you're looking for a place to clear your DGC exams, consider joining Wingman Aviation. We are an affordable ground school based out of Pune and provide one-on-one sessions, regular testing, and personalized lessons to make sure that you conceptually understand and ace your DGCA CPL exams. Also, if you're liking the content that we share here, don't forget to like, share, and subscribe for more exciting aviation content. Thanks for being a part of the Wingman community. Safe travels, happy landings, and I'll see you in the class again.